Okay, dear students, now let us continue. We are going to prove fundamental theorem of Galios theory. But before that, we will see a definition of Galios group. Then we will see again an exercise. And after that, we will enter into a new theorem. So the first definition we are going to see is Galios group. Let fx be a polynomial in capital Fx and k be the splitting field of f of x over capital F. Then this GKF is called the Galios group or Galios group, or some people also call this as Galba group of f of x over capital F. So if we are given a polynomial in fx and if k is the splitting field of this polynomial, then we have two fields, k which is an extension of f and f. Okay, then this GKF, you know the definition of GKF. It is collection of all automorphisms from k to k which fixes every element of f. So GKF, it is known as the Galios group of f of x over f. So given a polynomial and given k as the splitting field of the polynomial, GKF, that is known as the Galios group. Okay, so many times in examples, in MCQs or SQ, you may be given a polynomial and you may be asked to find out the Galios group of the polynomial. So all you need to do is find out the splitting field of the polynomial, and after finding the splitting field, you have to find GKF. Okay, for example, if you consider the polynomial x square plus 1, and suppose it is given in Rx, and you are asked to find the Galios group of this polynomial, GKF. Okay, or GKR in fact. So Galios group, find out the Galios group of this polynomial. That means you have to find out the splitting field of this polynomial, which you know is nothing but C. Okay. So now you have to find out the Galios group. That means what? You have to find out GCR, and GCR you have already found. You know that GCR is collection of two elements. First is identity, and the second one is the second one is the conjugate group, conjugate map. Okay, the map which sends a complex number to its conjugate, and sigma 0 is the identity. So that is the Galios group. So you may be asked to find out the order of the Galios group. It is nothing but 2. So this kind of questions are asked in MCQs and SQs. So please make sure that you know how to answer this. For example, you may be asked to find out this x square minus 2. Find out the Galios group of this polynomial. So all you need to find is the splitting field of this. It is nothing but q root 2, right? So now you have to find, you were asked to find the Galios group of this. So Galios group of this is nothing but g q root 2 over q. Okay, now you have to find this, and you know how to find this. You start with some sigma over here, then sigma is a map from q root 2 to q root 2 which fixes every element of q. Okay, now any map from q root 2 to q root 2 is of this form, a plus root 2b, and that is same as sigma of a plus sigma of root 2 and sigma of b. And because a and b are from q and sigma is automorphism which fixes every element of q, sigma of a is nothing but a and this is nothing but b, sigma of root 2. So all you need to find out is sigma of root 2. And so for finding out sigma of root 2, you will find sigma square of root 2. That is same as sigma root 2 into sigma root 2. You know this calculation that we have already done in class. This is same as root 2 into root 2, that is sigma of 2, that is nothing but 2. So sigma square of root 2 is 2. That means sigma square is plus or minus root 2. Okay. So sigma of root 2 is nothing but plus or minus root 2. So there are two maps in this. The one is the identity map, the other one is the map which sends a plus root 2b to a minus root 2b. Okay, so if you are asked to find out the order of this Galios group, it is nothing but again 2. This kind of problems are asked in MCQ and SQ, so make sure that you know this. And I would also like to say that please solve the SQ and MCQs in the previous question papers. And if you have any difficulty in solving any of the MCQs or SQs, then without any hesitation, please do contact. Okay, now let us. I will state an exercise, which again is a very simple, and I will give the solution to this exercise soon in this. In the team, I will upload the solution also. It is very simple, so we will not waste time in doing this problem. Let F, T, and K be fields with this relation that F is a subfield of T is a subfield of K. Okay, then it is easy to verify that T is a normal extension T is a normal extension of F if and only if sigma of T is a subset of T for every sigma belongs to GKF. Okay, so we will need this exercise in proving the fundamental theorem of Galios theory. So T is a normal extension of F if and only if sigma T is subset of sigma T is subset of T for every sigma belongs to GKF. Okay, so we will use this exercise in the next theorem, that is known as fundamental theorem of Galios theory. That's one of the important theorem. Fundamental theorem, important theorem in the sense of algebra. So fundamental theorem of Galios theory. So let us state this theorem. The statement is one of the biggest statements. Let f of x be a polynomial in capital Fx and capital K be the splitting field, and write in short as SF, splitting field of f of x over capital F. Okay, let GKF be the Galios group of f of x over capital F. Let us introduce some notations. F tilde. F tilde is what? It is collection of all the fields which lies between K and F. Okay, it is collection of all those fields T which lies between K and F. So F tilde is collection of all fields which lies between K and F. And H tilde, we consider H tilde as collection of all subgroups of GKF. Collection of all subsets which is a group, that means subgroup of GKF. Okay, so H tilde F tilde is clear. Now let us define a new map, that is lambda. Lambda is defined from F tilde to H tilde by lambda of T, where T belongs to F tilde. Lambda of T is GKT. Then you can observe that GKT belongs to H tilde. Okay, why GKT belongs to H tilde? Because GKT is a subgroup of GKF. That we have already seen. I have already proved in last. We have already discussed in last theorem that because F is a subfield of T, what is the relation between GKF and GKT? GKT is a subgroup of GKF. Okay, if this is the relation between F and T, then this is the relation between GKF and GKT. Okay, so you can clearly see that GKT is a subgroup of GKF, and hence this is an element of H tilde. So we have defined the map from F tilde to H tilde. Now, what we have to prove? We have to prove 6 statements. We prove one by one all the 6 statements. The first statement is T is same as fixed field of GKT. Fixed field of GKT, the T belongs to F tilde. Okay, this is the first thing that we will prove. I think instead of writing the statements, we'll prove. Let us first prove this first statement. Let us prove that T is same as GKT. That means fixed field of GKT is same as T. That is what we have to show. Okay. Now, let us observe the statement once again. Here, we are given a polynomial in fx, and we are given the splitting field of the polynomial. Okay. Then, by previous theorem, can you see that k is a normal extension of f? Because in last theorem, if you remember what we have proved, that k is a normal extension of f if and only if k is a splitting field of some polynomial over fx. That is what we have proved. K is a normal extension of f if and only if k is a splitting field of some polynomial over f. So here you can see that k is a splitting field of some polynomial over f. So what? K is a normal extension of f. So from the statement, it is already hidden in the statement that k is a normal extension of f using previous theorem. So let us start the proof with that. Note that k is a normal extension of f. Okay. Now k is a normal extension of f. That will imply that k is a normal extension of t also. Why? Let us observe that also. See, the same polynomial if you observe, because the polynomial is in fx, it is also in tx. Whenever you start with t belongs to f tilde, that means t is a extension of f, right? So fx belongs to tx also, right? And because fx belongs to tx, k is a splitting field of fx over t also, because we are not changing the polynomial, and hence the splitting field is not changed, right? We are only changing the base. Okay, fx over t, the splitting field is k itself, because we are not changing the polynomial, so the splitting field will remain the same. So you can see that k is the splitting field of a polynomial over t also. So again, using previous theorem, what I can say, because k is the splitting field of some polynomial over t, k is a normal extension of t using previous theorem. So k is a normal extension of f, and therefore I can also say that using previous theorem, k is a normal extension of t also. And because k is a normal extension of t, by definition of normal extension, what we have, dimension of k over t is finite, and fixed field of GKT, fixed field of GKT is same as t. Okay, this, so that means the first part follows from the definition of the normal extension. So you can see how easy this is. We can directly, in fact, we don't even need this. That was just for your information, I told. We can directly start from here that k is a normal extension of t. Why k is a normal extension of t? Using previous theorem, in order to prove that k is a normal extension of t, what I need to prove is k is a splitting field of some polynomial over t. You can see that if you consider fx, then fx belongs to tx, and k is the splitting field of fx over t. So that means k is a splitting field of some polynomial over t, and therefore k is a normal extension of t. So directly I can write that k is a normal extension of t, and hence by definition of normal extension, this is true. So we are done with the first part. So the proof of first part is. Now let us go for the second statement. H is the same as G K K H whenever H belongs to H tilde. That means H is a subgroup of GKF. What we have defined as H tilde. H tilde is collection of all subgroups of GKF. Because H belongs to H tilde, H is a subgroup of GKF. And if you remember, we have proved in theorem 4.2.3 that if K is a normal extension of F, then GKKH is same as H. Okay. Because of the previous theorem 4.2.3, I can directly say. But for that, the hypothesis is that K is a normal extension of F. The question is, do we have that? Yes, that is we have. K is a normal extension follows from this statement. K is normal extension of Fy, because K is a splitting field of some polynomial of F. So using previous theorem, I can say that, or this statement has a meaning that K is a normal extension of F. And because we have that K is a normal extension of F, using theorem 4.2.3, I can say that GKKH is same as H. That means the second statement is also done. GKKH is same as. So let us go for the third statement. What is the third statement? We have to prove that lambda is bijective. That means it is 1, 1 and on 2. Let us prove that this map lambda, which is defined like this, lambda of t is gkt, is bijective. That means we need to show that lambda is 1, 1 and on 2. So first let us prove that lambda is 1. So for that we need to start with two elements in the domain, t1 and t2, say. And suppose that lambda of t1 is same as lambda of t2. Then I need to show that t1 is same as t2. Lambda of t1 is nothing but gkt1, and lambda of t2 is nothing but gkt2. Now gkt1 and gk, if the groups are same, then the fixed field of the groups are also same, obviously. So fixed field of these groups, gkt1, is same as the fixed field of gkt2. The groups are same, then the fixed fields are same. That's why this is true. Now gkt1 we have proved in first. What does the first thing says? Gkt. Whenever I start with t belongs to f tilde, k gkt is same as t. So here you can know that t1 and t2 are from f tilde, and therefore k gkt1 is same as t1 and k gkt2 is same as t2. Using first, you can say that this is same as t1 and the second one is same as t2. This is because of 1. Okay, so t1 is equal to t2. So what I have proved, whenever the images are same, the elements are same, and therefore I can say that lambda is 1. Now let us prove that lambda is onto. Okay, so that means I have to start with an element of h tilde, and I have to prove that there exists an element in f tilde whose image is this element. Okay, so let us start with an element of h tilde. So let us start with an element, say h belongs to h tilde. So I have to construct some element whose image, lambda image, is nothing but capital H. Okay, so let us see what we can do. Okay, I have starting with one element of codomain. I have to construct an element of domain whose image is same as H. What element we can put here? Let us see. So because we are starting with H belongs to H tilde, that means what? H is a subgroup of GKF. H is a subgroup of GKF. And because H is a subgroup of GKF, we can talk about fixed field of H. So let us take fixed field of H over here. Let us see what the image of fixed field of H is. Okay, I have to because H is a subgroup, I can talk about the fixed field of H, and I will take that element in the domain. Okay, lambda of KH, I will prove that it is H. So lambda of KH, that by definition what it is? It is G. How is lambda defined? It is defined as GKT, right? Lambda of T is GKT. So lambda of KH is what? It is GKKH, right? And what is GKKH? We have just now observed that GKKH is same as H. Right? So this GKKH is same as H. So what I have proved? Whenever I start with an element of codomain, I can construct an element of domain whose image is H. Now the question is this an element of domain actually? Right? I have to check whether this belongs to f tilde, the domain. Domain of lambda is nothing but f tilde. So actually we have to check whether this kh belongs to f tilde or not. That means I have to check whether kh is a field lying between t and lying between k and f. See, the domain of lambda is f tilde. So I have to make sure that kh belongs to f tilde. That means KH must be lying between F and H, F and K. Can you see that it is true? Yes, KH is actually lying between F and K. Why is this true? KH is lying between. See, by definition, KH is what? It is the fixed field of K. So obviously it should be a subset of K. Now, will it contain F? The answer is yes. Why? Uh, See, what is KH? It is collection of all those elements of K which are fixed by every elements of H. Right? Now, elements of H are what? It is elements of H are also an element of GKF. Elements of GKF, that means they are automorphism which fixes every element of F. Okay, that means every element of H fixes F. Right? So F, every element of F is fixed by element of H. Therefore, F must be a subset of KH. See, all this follows by the definition of fixed field. Huh? And I hope that you know the definition of fixed field. Why F is a subset of KH? Because every element of F is fixed by every element of H. Why every element of H fixes every element of F? The reason is this, that H is a subgroup of GKF. And inside GKF, we know that GKF is collection of all those automorphism which fixes every element of F. So because elements of GKF fixes elements of F, all the elements of H also fixes all the elements of F. Therefore, all the elements of F are fixed by all the elements of H, and therefore F belongs to KH. F is a subset of KH. So you can see that KH is properly lying between F and H. And therefore, I can say that this is an element of codomain F tilde. So whenever we start with an element of domain, sorry, element of codomain, I can construct an element of domain whose image is the codomain. Okay, then would be ontoness also. What we have proved is lambda is 1 and onto. Now let us prove the fourth statement. In fourth statement, we have to prove that K T, dimension of K over T is same as order of GKT. And furthermore, we have to prove that dimension of T over F is same as order of GKF divided by order of GKT, which we will call as the index of GKT in GKF. Okay? We'll call this number as the index of GKT in GKF. So let us prove this statement. First, can you observe that this is true? See, because of theorem 4.2.3, K is a normal extension of F, then GKKH or dimension of K over KH is same as order of H. We have proved this theorem that K is a normal extension of F implies the first property is that dimension of K over KH is same as order of H, right? We have proved this. And where H is the subgroup of GKF, any subgroup of GKF. So whenever I replace H by GKF, what I have is KGKF, which is same as order of GKF. See, I can replace H by GKF because H is any subgroup of GKF. So I will take GKF as a subgroup of GKF. We have already discussed this. So this is true. So because of theorem 4.2.8, sorry, 4.2.3, K is a normal extension of F implies that this is true. And because K is normal extension of F, this quantity is nothing but the whole F. So dimension of K over F is same as order of GKF. So whenever K is a normal extension of F, what we can conclude is that dimension of K over F is same as order of GKF. Okay. Now, in the first part only, we have observed that K is a normal extension of T also. While proving the first statement, we observed that K is a normal extension of T. It is still true here. Why k is a normal extension of t? Because k is a splitting field of some polynomial over t. What is a polynomial? In fact, the given polynomial fx. It is a polynomial over t, right? And splitting field is k. So I got some polynomial from tx whose splitting field is k. So I can say that k is a normal extension of t. So we have already that k is a normal extension of t. Okay, and that will imply dimension of k over t is same as order of gkt. Okay, and that is what we have to prove here. Dimension of k over t is same as order of gkt. So first part is true because k is a normal extension of t. So we have proved already this part. This part is because of the normal extension of, because k is a normal extension of t. Okay, now again this equality can be easily proved, easily observed. Let us see how why. See, now already we know that k is a normal extension of f. That implies order of gkf is same as the dimension of k over f. Okay, so order of gkf is dimension of k over f. But we know that t is lying between k and f, so I can split this as dimension of k over t into dimension of t over f. Okay, now what is dimension of k over t? We have just now proved that it is order of gkt. So order of gkt into dimension of t over. So I can make this as subject now. So what is dimension of t over f? It is nothing but order of gkf divided by order of gkt, which is same as dimension of t over f. So again you can see that we have proved this. So dimension of t over f is same as order of gkf divided by order of gkt. So again we are done with the fourth part. Okay, now let us move forward to the fifth statement of Galios theory. In the fifth statement, we have to prove that this is quite important statement. So please pay attention. K, if K belongs to F tilde, if T belongs to F tilde is a normal extension of F if and only if GKT is a normal subgroup of GKF. So see the relation between normal extension and normal subgroup. So that's why this is very important statement which was given by Galios. So it is known as fundamental theorem of Galios theory. It establishes the relation between normal extension and normal subgroup. Normal subgroup concept you already know, you have studied in BSc. Normal subgroup. Okay, so why the extension is called normal extension? Because it has something to do with the normal subgroup. That's why the name was given the same, normal extension and normal subgroup, because there is a relation with this is the in fact the relation between the normal extension and the normal subgroup. I hope that you remember the definition of normal subgroup. We say that H is a normal subgroup of G. When can we say that H is a normal subgroup? The definition is if and only if whenever I start with H belongs to H and G belongs to G, what happens? G inverse HG also belongs to capital H. This is the definition of normal subgroup. Okay, so remember or let us recall the definition of normal subgroup. Okay, we have recalled the definition of normal subgroup. Now let us go. So we have to establish this relation now. To start with the proof of this relation. Let us first assume that T is a normal extension of F. Assume that capital T is a normal extension of capital F. Okay, because capital T is a normal extension of capital F, using the previous exercise, what I can say, remember this exercise because I will be able to show you once again and again. Once I'll show you K is a T is a normal extension of F if and only if sigma T is subset of T. Okay, we already know this thing. T is a normal extension of F if and only if sigma T is subset of T. So now we are assuming here that T is a normal extension of F. Therefore, by exercise, what we can say? Therefore, by exercise, uh, we can say that sigma of T is a subset of T for every sigma belongs to GKF. Okay, and now what we have to prove? GKT is a normal subgroup of GKF. That means if I start with an element of GKT and an element of GKF, let us say start with an element of sigma as an element of GKF. So let sigma belongs to GKF and tau belongs to GKT. Okay, then I need to prove that in order to show that GKT is a normal subgroup of GKF, I need to prove that sigma tau, sigma inverse tau sigma, sigma inverse tau sigma. So this is now our claim. Okay, what? That sigma inverse tau sigma belongs to GKT. If we are able to show this, then we are done. Then it is true that GKT is a subgroup of GK. So all I need to prove is that sigma inverse tau sigma belongs to GKT. When will sigma inverse tau sigma belongs to GKT? We know that GKT is collection of all those automorphism from K to K which fixes every element of T. So I need to prove that this is already an automorphism from K to K, right? Because sigma is an automorphism from K to K and tau is also an automorphism from K to K. So obviously sigma inverse tau sigma is an automorphism from K to K, that is clear. Now we all need to prove is that it fixes every element of T. I need to prove that sigma inverse tau sigma fixes every element of T. So let us start with an element of T and we will prove that sigma fixes this element fixes that T. So let T belongs to capital T. Okay, I already know that tau fixes every element of T, right? Then what I can say is that tau of T is same as but we don't need this actually. Let us use this. See, because T belongs to capital T, sigma of T also belongs to capital T because it is because of this exercise. See, sigma of T is subset of T. That means sigma sends every element of T to itself. So, every element of T to an element of T. Right? Sigma, what is sigma doing here? Sigma sends every element of T to another element of T. So if I start with an element of T, sigma T will send it to sigma T because of this exercise. So sigma T is an element of T. Now I know that tau fixes every element of T. So this is an element of T, so tau will fix this element. Therefore, I can say that tau fixes sigma T. Okay, and this will imply that sigma inverse tau sigma of T is same as T. And this is true for every T because we started with arbitrary and we show that this is true. So what I have proved here is sigma inverse tau sigma fixes every element of T. Okay, so sigma inverse tau sigma is an automorphism from K to K which fixes every element of T. Right? So therefore, from this I can say that sigma inverse tau sigma belongs to GKT. Okay, so I proved this claim that means GKT is a normal subgroup of GKF. Now let us go for the converse part. Conversely, assume that GKT is a normal subgroup of GKF. GKT is a normal subgroup of GKF. Then I need to prove that. What is our claim now? that T is a normal extension of F. That is now our claim, right? T is a normal extension of F. In order to prove that T is a normal extension of F, using exercise, I just need to prove that sigma T is subset of T for every sigma belongs to GK, right? So our claim actually is to prove that T is a normal extension of F. But using exercise, what I need to prove, that is I need to prove that, or that is our claim is that sigma of T is a subset of T for every sigma belongs to GK. Okay. Now I just need to prove this, that every element of GKF sends element of T to itself. Element of T to T. Let us start with an element of GKF. Let sigma belongs to GKF. Okay. And let us start with an element of T also. Let T belongs to T. So I need to prove that. So now our claim is that uh, sigma of T is in T. Okay, I need to just prove that sigma of T is in T. For that, let us see what we can do. Now, if I start with tau belonging to GKT, then because GKT is a normal subgroup of GKF, what I can say is that sigma inverse tau of sigma belongs to GKT. What is the reason here? That GKT is a normal subgroup of GKF. That's why I can claim this, that if T belongs to GKT, then sigma inverse tau sigma belongs to GKT, because GKT is a normal subgroup of GKF. So this belongs to GKT. That means sigma inverse tau sigma fixes every element of T, right? And therefore I can say that sigma inverse tau sigma, because it fixes every element of T, in fact it will also fix this small t. So what I have is this, because sigma inverse tau sigma fixes every element of T. This is an element of T, so it is fixing that element. Okay. So from this I can observe that tau of sigma T is same as sigma. Whenever I compose both sides by sigma, here sigma inverse and sigma will go, and here I'll have sigma. So what I have observed is tau fixes sigma T. Any tau belongs to GKT fixes sigma T. That means every element of GKT is fixing sigma T. So what I can say is that sigma T belongs to fixed field of GKT. Right? Fixed field of GKT means what? All those elements of K which is fixed by every elements of GKT. And I have seen here that if I start with an element of GKT, it is fixing sigma T. So every element of GKT is fixing sigma T. So I can say that my sigma belongs to K, fixed field of GKT. Now what is fixed field of GKT? This is same as exactly T, because K is a normal extension of T, right? It is already there. K is a normal extension of F, and hence K is a normal extension of T. We have used that in first part also. So K normal extension of T already we have. Because K is a normal extension of T, by definition of normal extension, I have that K GKT same as T. So what I have proved, sigma T is an element of T, and that's what my claim was. I proved that sigma T belongs to G. So what I have proved, my claim. That means we have proved T is a normal extension of F. Normal extension of F, and hence we are done with this statement that T is a normal extension of F if and only if GKT is a normal extension of GK. Okay, now let us go to the last statement of the fundamental theorem of Galios theory. The last statement, the sixth statement, is that T is a normal extension of F implies, or then if T is a normal extension of capital F, then GKF quotient with GKT is isomorphic to GTF. This is again an interesting theorem. If T is a normal T is a normal extension of F. If T is a normal extension of F, then GKF quotient GKT is isomorphic to GTF. For that, we will use some definition, some map. So let us first assume that K is a normal T is a normal extension of F. So assume that capital T is a normal extension of. Now I need to show that GKF quotient GKT is isomorphic to this. For this, let us first define a map. Define a map phi from GKF to GTF by how we will define? We will define phi of sigma is same as sigma restricted to T. Restriction function we are using here. You know that what restriction function is. It is the restriction of the domain. See, what is the domain of this sigma? Because sigma belongs to GKF. What is sigma? Sigma is an automorphism from K to K which fixes every element of it. So that means what is the domain of sigma? The domain of sigma is K. And what I am doing here, restricting the domain of sigma from K to T. So here we are restricting the domain. Here the domain of sigma is K, but here the domain of sigma is T. We are not changing the definition. We are just restricting the domain. The domain of the old sigma was K. Here the domain of the new sigma restricted to T is T. Okay, we are restricting the domain. We are not changing the definition of the function. We are just restricting the domain. So I am defining like this. It's obvious that if sigma is an element of GKF, then sigma restricted to T, because the domain has been restricted, it's an element of GTF. So now we'll show that using first homomorphism theorem, we will show this result. Okay. It is easy to check that. We can easily check that this phi will form a group homomorphism. Okay, so I can use first homomorphism theorem. What is the first homomorphism theorem stating? That it states that GKF. See, because this is an homomorphism, first homomorphism theorem says that GKF quotient kernel of phi is isomorphic to image of GKF. See, if the map is onto, then I can replace this image by codomain. We can replace this range by codomain. But provided I should know that phi is onto or not. Right now, we don't know whether phi is onto or not. We just know that phi is an homomorphism. Therefore, using first homomorphism theorem, we are using here first homomorphism theorem. Okay, so using first homomorphism theorem, GKF quotient kernel phi is isomorphic to this. But actually, what we have to prove is GKF quotient GKT is isomorphic to this. So I will somehow prove that this kernel is same as GTF GKT, and this phi of GKF is same as GTF. We will prove both of this equalities. Kernel phi is same as GKT, and phi of GKF is same as GTF. If we are able to prove this, then we are done. So let us first prove that the kernel is nothing but GKT. Okay, so let us start with an element of kernel phi. Say suppose sigma belongs to kernel phi. Then that will imply that because phi is in sigma belongs to kernel of phi, image of this sigma is an identity. Is identity. Identity where? In the codomain, right? GTF. It is an identity of GTF. Now, what is sigma? Phi of sigma? It is nothing but sigma restricted to T. So sigma restricted to T is an identity of GTF. So sigma restricted to T is an identity. That means what? It fixes every element of T, right? So in that case, I can say that because see the definition of sigma T and sigma is same. We are just restricting the domain, right? So because sigma t restricted to t, sigma restricted to t is identity of GTF. That means it fixes every element of f. Sorry, it fixes every element of t. So that means I can say that sigma belongs to GKT because sigma is a uh, automorphism from K to K which fixes every element of T. Why it is fixing every element of T? Because it is an identity. Sigma restricted to T is an identity. That means on T it will behave as identity. It fixes every element of T. And because the definition of sigma restricted to T and definition of sigma are same, and because this sigma fixes every element of T, this sigma must also fix every element of T. That means this sigma is a map of GKT. That means I proved that every element of kernel is same as element of GKT. So what we have actually proved is kernel of phi is same as GKT. So you can see that we have proved the first equality, that kernel of phi is same as GKT. So all I need to now prove is that GTF is same as phi of GKF. We'll prove this in a unique way. That means in short we have to prove that phi is a uh, onto map. So now what we have, GKT using first homomorphism theorem, GKT quotient of kernel, but kernel is now proved to be GKF, right? GKT. GKF, right? So what we have, GKF, right? I am just putting the value of kernel phi. That's it. GKF quotient kernel phi is isomorphic to it, right? So GKF quotient kernel phi. GKF quotient kernel phi, but kernel phi is nothing but GKT, and that was isomorphic to what? Phi of G of GKF. Okay, we have this equality. So because this both groups are isomorphic to each other, the elements, the order of the group is same. So order of this quotient group GKF, quotient with GKT, is same as the order of this range GKF. So what I have proved, order of this quotient group is same as this because both the groups are isomorphic. This is quotient group, okay? So this quotient group is isomorphic to this group, and therefore the order of both the groups are same. And we know that order of quotient group, G quotient H. What is the order of G quotient H? It says that its order is order of G divided by order of H by using Lagrange's theorem. You remember you have proved this in BSc, okay? So the order of the quotient group is nothing but order of the group this divided by order of GK, because order of G quotient H is same as order of G divided by order of H. This is same as order of phi of GKF. Okay, order of G this is. Now we have proved in the fifth part, fifth or fourth. Yeah, in fourth part we have proved that order of GKF divided by order of GKT is same as dimension of T over F. Dimension of T over the dimension of T over F is now same as order of phi of GKF. But order of phi of GKF is what? It is a subgroup of order of GKT. GT order of GT. Why is this true? Because phi of GKF. See, phi of GKF is a subset of GTF. Right? Phi of GKF means what? It is the range. Range is always subset of codomain, right? So this is true. And what is this? Because T is a normal extension of F is already given. This is same as dimension of T over F. So you can see that this has become a sandwich, dimension of T over F and dimension of T over F. So that means the order of the range and the order of codomain are both same. So that means order of the range and the order of codomain are same. Because both are finite groups, we must have the range is same as the codomain. Because if you are dealing with a finite group, and if order of the subgroup and the order of groups are same, then subgroup must be same as the group. There is no other option, right? So what I have proved is order of GKF is same as, sorry, phi of GKF is same as GTF. So now let us again substitute that over here. We have proved that this is same as GTF. So that is the required thing that we need to prove, that order of GKF quotient GKT is isomorphic to GTF. That's what we have proved. So we are done with the here. So we have proved each and every statement of the fundamental theorem of Galios theory. So we are done with the fundamental theorem of Galios theory. If you have any doubt in this theorem after seeing this video, then please